Let's now consider the situation where we have a finite sample space omega and where all the outcomes in omega are equally likely. In that case, intuitively, the probability of an event A is simply the number of elements in the set A divided by the number of elements in the sample space omega. In other words, to compute the probability of A, we need merely count the number of elements in A. One very useful but obvious principle that we will use again and again here is the so-called multiplication principle. It states the following: if one random experiment has m possible outcomes and another experiment has n possible outcomes, then the combined experiment has m times n possible outcomes, i.e. there are m times n possible combined outcomes for the two random experiments. Here's an example to make clear what I mean by that. Suppose you toss a coin and then roll a die. For the coin toss, there are two possibilities, heads and tails, and for the roll of the die, there are 6 possibilities, the numbers from 1 up to 6. And hence there are 2 times 6 equals 12 possible outcomes for the combined experiment of tossing a coin and rolling a die. And those possible outcomes are heads and 1, tails and 1, heads and 2, tails and 2, etc. Another example, in an ordinary pack of cards, the cards have 13 possible values, namely the numbers from 2 up to 10, followed by Jack, Queen, King and Ace. And there are 4 suits, namely diamonds, clubs, hearts and spades. Hence there are 13 times 4 equals 52 cards in a pack. Just some notation, recall that if n is a non-negative integer, then n factorial is defined to be the product of all the numbers from 1 up to n. So for example, 3 factorial is just 1 times 2 times 3, and that's 6. Also note the following important convention: 0 factorial is defined to be equal to the number 1. Let's now consider the number of ways in which you can select an ordered sample. Suppose you want to select an ordered sample of m elements from a set which has n elements. And suppose that you sample with replacement. And by this I mean that you can select the same element again and again. In that case, the number of ways in which you can select m elements from n is n to the power m. In order to show this, we use the multiplication principle. Firstly, there are n choices for the first element. Because we may choose that element again, there are still n choices for the second element. Then there are n choices for the third element, etc., until finally there are n choices for the mth element. And thus by the multiplication principle, there are a total of n times n times n, where there are m factors, i.e. n to the power m possibilities. Next, suppose you sample without replacement. This means that you can select each element only once. In that case, the number of ordered samples that you can choose is given by n times n minus 1 times n minus 2 all the way down to n minus m plus 1, which is equal to n factorial over n minus m factorial. Just to see why, note that n times n minus 1 times n minus 2 all the way down to n minus m plus 1 is the same quantity multiplied by 1, where 1 is expressed as a product of the numbers from n minus m all the way down to 1 divided by itself. In that case, at the top, you have all the numbers multiplied from 1 up to n. In other words, at the top you have n factorial. And at the bottom you have all the numbers multiplied from 1 up to n minus m, i.e. n minus m factorial. We derive this quantity as follows. There are n choices for the first element. Since we can't select that element again, there are only n minus 1 choices for the second element. Then there will be only n minus 2 choices for the third element, etc., until finally there are only n minus m plus 1 choices for the mth element. And so by the multiplication principle, a total of n times n minus 1 all the way down to n minus m plus 1 possibilities, where there are m factors. Some quick examples. The number of 4-letter words that can be made with the 26-letter alphabet is 26 to the power 4. On the other hand, the number of 4-letter words that can be made if you may use each letter at most once is 26 times 25 times 24 times 23. A permutation of a set is simply a reordering or a rearrangement of that set. Using the multiplication principle, we see that there are n factorial many ways of rearranging the objects of an n-element set. There are n choices for the first element, then n minus 1 choices for the second element, etc., all the way to n minus 1 choices for the nth element. And that's a total of n times n minus 1 all the way down to 1 equals n factorial possibilities. Up to now, we have considered ordered samples, i.e. samples where it matters in which order the elements are selected. Consider now unordered samples, where the order in which we select the elements is not important. In that case, there are n combination m, which is defined to be n factorial over m factorial times n minus m factorial, many ways of selecting an unordered sample of m elements from a set which has n elements. Notice that this quantity over here can also be written as follows: n times n minus 1 times n minus 2 all the way down to n minus m plus 1, divided by 1 times 2 times 3 all the way up to m. So at the top we have m many factors, starting from n going all the way down, and at the bottom we have also m many factors, starting from 1 all the way up to m. To see this, note that we have just seen that there are n factorial over n minus m factorial many ways of selecting an ordered sample of m elements from n. However, each of those samples can be rearranged in m factorial many ways, because there are m factorial many permutations of each such sample. If the order in which we select the sample does not matter, then each such sample is counted m factorial many times, and thus the total number of unordered samples is n factorial divided by n minus m factorial divided by m factorial, which is precisely n combination m. An example will serve to make the above argument clear. In the South African lottery, a player must select 6 numbers from 1 up to 52, and will win the jackpot if the player's numbers correspond to those randomly selected by lottery officials. The order in which these numbers are selected does not matter. So, for example, 42, 33, 11, 25, 46 and 34 yields the same payoff as 11, 25, 33, 34, 42, 46, or any other permutations of these 6 numbers. This specific set of numbers could have been chosen in 6 factorial many ways. There are 6 factorial many ways of rearranging this set of numbers. On the other hand, there are 52 times 51 all the way down to 47, which is the same as 52 factorial over 52 minus 6 factorial, many ways of choosing an ordered sample without replacement of 6 lottery numbers. But each of those samples could have been chosen in 6 factorial many different ways. Each unordered sample is therefore duplicated 6 factorial many times. Hence the number of unordered samples of 6 lottery numbers is 52 times 51 down to 47 divided by 1 times 2 up to 6, which is just 52 combination 6. And that's over 20 million many ways. The probability of winning the jackpot is therefore less than 1 in 20 million.